Okay, welcome back to the lecture on digital signal processing. So far, what we have discussed in this lecture would include Z transform with its property. Then we discussed discrete time Fourier transform with its property, and later on we have also discussed discrete Fourier transform with its properties. We had also discussed filter designing and its transformation technique from low pass to high pass and high pass to low pass, vice versa. And we had discussed frequency analysis, frequency response, how those things work. All these topics had been covered before our mid breaks. After mid break, we had to discuss our one topic would be on fast Fourier transform. Basically, it's similar to discrete Fourier transform. And later on, once we complete fast Fourier transform, then we'll move toward filter structure and filter designing. Okay, so those of you guys who don't remember the previous lecture, you have to revise those lectures so that we would be able to understand. For studying fast Fourier transform, you need to study discrete Fourier transform, as fast Fourier transform is completely the same thing as discrete Fourier transform. It's just the way by which we can compute our answer in a quicker process. As the name describes it, it's fast Fourier transform, so we can perform Fourier transform through it. The same answer that we get from discrete Fourier transform, we can extract those answers, but this technique is a little bit quicker. So those of you who don't remember anything about discrete Fourier transform, first go back to your lecture on discrete Fourier transform, revise its content, learn how we get Wn. Once you have those ideas in your mind, then return to your lecture on fast Fourier transform. Now, most of you guys would remember what this formula means. This is the basic formula for discrete Fourier transform that we had discussed, where we had an exponential term, and that exponential term had two unknown variables, k and n, which need to be varied. We had already discussed that these two variables, k and n, need to be varied from 0 to n minus 1. That would mean that k variable would have a total of n sample, and similarly the n variable would also have n amount of samples. What we studied in discrete Fourier transform was that we change our exponential term into this Wn term. And to calculate the Wn term, what we did was that we draw a unit circle and distribute our n points in the unit circle and calculate different value of Wn. We will do that later on when we will be performing fast Fourier transform. So this technique would be showed, but this was the basic idea behind fast Fourier transform. Now, as I have told you, fast Fourier transform is a technique by which we can perform discrete Fourier transform. The only advantage that we have with fast Fourier transform is its speed. So let's discuss how faster fast Fourier transform is. If you are trying to calculate discrete Fourier transform of a system, basically how we did that was we start by considering that our system k is equal to 0. We suppose that. And then if k is equal to 0, our formula would be changed to n is equal to 0, upper limit would be n minus 1, x of n, and this variable would be Wn, and its power would be 0. Now, power of anything when it's equal to 0 Wn power of anything when it is equal to 0 is equal to 1. So this variable Wn0 would be equal to 1. Now what we have to do is we have to vary the values of n. First we will place n is equal to 0. We will get some value at that point. Then we need to place n is equal to 1. We will get one value at that point. And so forth. We will keep on varying variable until we get n is equal to n minus 1. Small n is equal to capital N minus 1. So for when our k was equal to 0, we had to, the answer that we get, or our x of k, that to calculate that we have to perform n different amount of computations. Similarly, when k would be equal to 1, our formula would change to n equal to 0, n minus 1, x of n, w n, small n. Now, as n keep on changing, like we would have value of n when it would be 0, then n would be 1, small n, I am talking about so small n, 0, 1, 2, it will keep on varying until we get to n minus 1. So to get the value when k is equal to 1, we need to perform capital N complex multiplication. Similar technique would keep on happening. We will place k is equal to 2, k is equal to 3 until we get k is equal to n minus 1. And for that, when k is equal to n minus 1, we again need to perform n computation. So for each value of k, we have to perform n computations, and the total value of k are also n. So in total, we have to perform n square complex multiplication. To get a value of DFT, we basically need to perform n square complex multiplication. Whereas when it comes to addition, if we look at some formula like this formula, like the second formula, when k was equal to 1, for that, if we look at that, what we have to do, we have to sum complete n variable. We need to sum that, and we need to perform that n minus 1. So in total, we also need to perform n into n minus 1 complex addition. So to perform DFT, we have to perform n square complex multiplication and n into n minus 1 complex addition. Now, how FFT is better than that is that it reduces our complex computation with the help of this formula, where we use log 2n. Now consider, if we have 1024, we need to calculate DFT when n is equal to 1024. For that, if we are calculating the Fourier transform when n is equal to 1024 using DFT, how many complex computation we need to perform? That will be 1024 whole square. That is approximately equal to 1 million complex computation. Whereas if we perform n is equal to 1024 using FFT, the complex computation would be reduced to 512 log 2n 2 raised to power, basically 2 raised to power 10 is equal to 1024. So what we will place over here would be 10. So our answer would be 5120. That would be 5120. So when n was equal to 1024, we have to, while performing DFT, we need to perform 1 million complex computation, whereas FFTs reduce the number of complex computation to 5120. Now in practical scenarios, if we take some practical example, over there we have a lot of variable sample. Let's consider, let me first clear this slide and then repeat what I'm saying. Here is all on the side. Yeah. Let's take a practical example. Consider if we are taking FFT of a 1 second audio signal. Now the frequency at which a human can hear, or a nominal audible voice for a human, that is approximately equal to 4.4 kilohertz. That would mean that it is 4400 hertz. Now in the first lecture I told you, according to Nyquist-Shannon theorem, what we have to do, if we need to sample some system, we have to sample it twice of your maximum frequency. According to that theorem, our sampling frequency would be equal to twice of your frequency, that is 8800 hertz. That would be your sampling frequency. Now as the signal is for 1 second, that would mean that our total samples would be equal to 8800 samples. Now if we are performing DFT on that system, what that mean? That would mean that n is equal to 8800 just for 1 second sample frequency. I'm talking about 1 second audio signal. For that our n is equal to 8800. When we perform DFT on that system, that would be equal to 8800 square. The answer that we will get is 77 million complex computation. Whereas if the same sample Fourier transform is calculated, the answer that we will get would be 4400 into 13, which is equal to 57,000 complex computation. So we can see, if we are performing Fourier transform for just a 1 second sample, and to calculate that Fourier transform, if we are using discrete Fourier transform, we have to perform 77 million complex computation, whereas in fast Fourier transform we just need to perform 57,000 computations. Now the Fourier transform basically has the same application as discrete Fourier transform, but its major advantage over discrete Fourier transform, as we are discussing this as an independent topic, it would have an advantage over discrete Fourier transform. The major advantage is that its speed, the speed of computation. If we are performing some computation, usually our speed matters a lot, and for that fast Fourier transform is lot advantageous. Now if I gave you, although I have told you already, I have told you the advantages of discrete Fourier transform, but let me remind you some advantages so that you can see how discrete Fourier transform was advantageous and how fast Fourier transform enhanced those advantages by reducing our computation time. first application for discrete Fourier transform would be related to your open-ended lab. In an open-ended lab, I have provided you where you need to tune your guitar. Every guitar have not every guitar, but the basic guitar usually have 6 strings that are named as A, B, C, and so on and so forth. And when you pick a string, it generates a specific frequency. To detect that frequency, what we perform is known as discrete Fourier transform. Now, for your open-ended lab, what I marked is that you should take a sample for around 5 seconds. As you have already seen, just for 1 second, when we are performing DFT, we have to perform 77 million computation. And for FFT, we just need to perform 57,000 computation. So for a 5-second sample, this time reduction would be increased by 5 times. So for your open-ended lab, try to use fast Fourier transform rather than using discrete Fourier transform. Second advantage would be in industry. Industry usually have way big motors and devices like that. All those devices produce vibration. Using the vibration, like if you are working with your motor, using the vibration analysis, we can identify the type of fault. Like if your motor bearing or its shaft or its gearbox, if it has some crack on it, by the variation of vibration analysis, we can identify the position or the type of crack on the place where it is, like if it's on bearing or on the shaft or on the gearbox. To calculate that using vibration analysis, what we perform is that we perform FFT on our vibration analysis. So our first example was related to our coursework. Our second example is related to industry. Now moving towards the third example, that could be basically related to your final year project. What we can do is, it's not specific that you have to perform something like that. You can innovate different idea, but I'm giving you an idea for a final year project. Is that if you start your car, if your engine and everything is perfectly fine, it would generate different set of frequencies. But if there is a fault in your car, like your belt or something is squeaking or is lacking with oiling or something like that, it would generate a different set of frequencies. And those frequencies could be calculated using fast Fourier transform. So if you have a proper speaker that can detect every range of frequency, and when you perform fast Fourier transform on your audio signal, you can directly detect the type of fault within your vehicle. This is an application for fast Fourier transform. You can think of way more ideas. In internet, numerous examples are provided. You can view those examples, but these were basic 3 examples that would be related to your course project, industry, and your final year project. Okay, so we have discussed what fast Fourier transform was. Basically, what it not, we haven't discussed what it is, but we have discussed its application. Now what we have to discuss is what Fourier transform is. What did we do so that we can decrease our computation time? The indigenous idea behind fast Fourier transform was introduced by Coué method. Later on, it was improvised by different people, and the idea that I am giving you is known as Radix 2 method. What we do in radix 2 method is that for a series, if we need to perform fast Fourier transform, we basically divide it into two equal parts. First part would be all your even entries, and the second part would be all your odd entries. For example, and as an example, I would keep on taking, for all example, I would be taking 8-point DFT. For uniqueness and similarity, I would keep on using, in every example, I would be using 8-point DFT. So for 8-point DFT, what would that mean? That we have to distribute the system into even and odd part would be that if our series, if we want to write our series, how we will write it is x of 0 would be our first term, then we would get x of 1, then we will get x of 2, and this term would keep on increasing until we get x of 7. Now, what would be its odd and what would be its even part? Let's discuss its even part. Even part would be the number that would contain even entries. That would mean x of 0 is our even part, x of 2 is our even part, x of 4 is our even part, and x of 6 is our even part. That would mean that we will leave one entry that would represent our odd part, and our even part would contain even numbers. Similarly, our odd entries for this term, this series would be x of 1, x of 3, x of 5, and x of 7. So in such similar manner, what we have done is that we have distributed our function into two equal parts, even and odd part. To represent a function in even part, what we have to do is that we suppose n is equal to 2m. In this form, we will always represent even entries. And for odd function, what we do is that we suppose n is equal to 2m plus 1. In this manner, we will always represent odd entries. The same ideology that I have told you is performed in the next equation. The only thing that happened is that our upper range of summation in the initial formula was n minus 1. Now it is reduced to n by 2 minus 1 as our number of points has been decreased to half. Half of those variables would be available in even entries, and the rest half would be available in odd entries. Now mathematically, what we can do over here is that we can represent this omega n 1k out of our summation. We can move this to omega n raised to power k out of this summation. The same thing have been done over there. Omega n k was moved out of the summation, and the rest is written in a similar manner. Now, to show the trick, what FFT does, I have to open a blank page and explain it to you over there. Now, screen white page. Okay. Now for calculating DFT, basically what we did was that we draw a unit circle. This is not a proper circle. I'm not good at drawing, so apologies for that, but try to consider that it is a circle and it is uniformly distributed on x and y axis. So as I have told you, I am taking for example n would be equal to 8, so I am calculating DFT for 8 point. As this is the DFT for 8 point, what we have to do is that we have to distribute our circle into 8 equal parts. So that would mean after 45 degrees we will get our next point. So according to that, this would be equal to W80. Our next variable over here would be equal to W81. This value be equal to W82. Our next variable over here would be equal to W83. This variable is W84. This variable would be W85. Now our y-axis would be equal to W86, and the last variable would be equal to W87. Now W88 would be equal to over here, so it would be equal to W80. This was basically the diagram for calculating 8-point DFT. Now let's redraw the diagram for calculating 4-point DFT. Let me change the color of the marker so that I can show you. Let's change something to blue. Okay. Yeah, it's blue. I'm calculating 4-point DFT. Now for 4-point DFT, what we have to do is that we have to distribute the unit circle into 4 equal parts. So this point would be equal to W40. This point would be equal to W41. This point would be equal to W42, whereas this point would be equal to W43. Now, according to this, what we can see is that W40 was equal to W80, whereas W41 was equal to W82, whereas W42 was equal to W84, and W43 is equal to W86. Now, using these analogies, what we can think of in a general form, what we can write would be something like this. When we have W raised to power m n by 2, we can equate it equal to W of n to m. Let's test this example over here. W of n to m would mean W of 8 2. That would mean n is equal to 8 and 2m is equal to 2. That would mean our m is equal to 1, whereas n by 2 would be equal to 4. So what we can write over here would be W of 4 raised to power 1. So using this formula, our ideology of FFT was introduced. Now try to think of this formula, try to remember this formula and see what we did in our previous slide, how we will change things, and we can see how fast Fourier transform was introduced. Now in this formula we had W and 2 over into mk. Using the same transformation we did convert this Wn to Mk into Wn by 2 Mk. Similarly, this transformation was also transformed into that form. Now, if you think of this formula, what we have done over here is that we have reduced our FFT terms or distributed our FFT term into two equal parts. Let's move to the, let me discuss over here, then we will move to the next slide. Okay. Now, what we were doing previously in initial example, we were calculating 8-point DFT as an example, and over here what we get is that this is W4 MK and this is also W4 MK. So what we can see over here is that basically this is the formula for 4-point DFT. When we were calculating 4-point DFT, we used this formula. And similarly, this is the formula for 4-point DFT. The first formula is the 4-point DFT for even entries, whereas the second formula is the 4-point DFT for odd entries. So what we did is divide and conquer rule. We used divide and conquer rule. The series that was of 8 terms, we divided it into four 2 terms and simplified our series. How timing is reduced, computation timing, how that is reduced, we will discuss that on the next slide once we will completely understand what's happening over here. After that, we will see how computation time is reduced. But let me show, first of all, let me show what this equation means over here. The interesting thing over here that we need to remember while drawing our diagram would be that basically this and this is over here we have n by 2 for 8-point DFT. What we will get would be W4 term over here, whereas W4 term would be used over here, but over here we use W8 term. Try to remember that, because this is a common mistake that usually people make when drawing butterfly diagram. Butterfly diagram, we use butterfly diagram to describe this equation. We will do that in the next slide, but try to remember that for one term we have W4 and for the other we have W8 term. So we can represent this equation as we have represented over here, where f of k would be the 4-point DFT of even entries, and we represent g of k as the 4-point DFT for odd entries, and the w and k part remain as it is. Now, showing this in terms of a diagram, we will do that on the next slide. Let me write down the formula for you so that we can use that. Our formula is basically x of k is equal to g of k plus w8 k oh sorry, it was f of k over here. We will write down f of k over here. F of k, whereas this term was g of k. Now, what we are doing over here is that f of k represent 4-point DFT of even entries. What we have over here in the start would be all the even entries, and what we have performed in this block is the DFT of those 4 even entries, and our answer would be these 4 terms: F0, F1, F2, F3. These are the 4-point DFT of even entries, whereas our odd terms are written over here and its 4-point DFT are represented as G0, G1, G2, G3. Now, according to this formula, what we have to do is that we need to add those terms, whereas we need to multiply W8 of k with G of k term. Now, if we are trying to calculate x of 0, what would that mean in formula term? We can write x of 0 would be equal to basically f of 0 plus omega 80 g of 0. So what we have to do is we can multiply g of 0 term with W80 and add that term to f of 0. This W80 term is multiplied by g of 0 and then this is added with f of 0. Similarly, for x of 1, what we will get, this 0, this 0, this 0 and this 0 term would be replaced with the term 1. So what we will get, our answer would be g of 1 multiplied by W8 of 1 plus f of 1, which can be seen over here, g of 1 multiplied by W8 of 1 plus f of 1. Similarly, x2 and x3 terms would be calculated. Now the x4 term, this is the interesting term, as we don't have any term known as f4 and g4. How would we calculate x4? As all these terms are the value for DFT, now try to rethink what DFT was using a unit circle diagram. In unit circle diagram, if we were representing this as f of 0, the second term was, as this is 4-point DFT, the second term over here would be f of 1, the third term would be f of 2, the fourth term would be f of 3, the fifth term would be f of 4. So what we can see is that according to DFT, f of 0 is equal to f of 4. So for x of 4, what we can do is write down the formula like x of 4, f of, we have to use f of 4 over here, but f of 4 is equal to f of 0 plus W84, as this is the term for 8-point DFT, hence W84 would not be equal to W80, but F4 would be equal to F0. Similarly, the next term would be G of 4, but as we know, G4 would be equal to G of 0. So we will write our next term X of 4 using this transformation technique. Our X of 4 is equal to G of 0 is multiplied by W at 4 and then added with X of 0. Similarly, we can calculate X5, X6, X7 term over here. So basically what we did over here is that we calculated an 8-point DFT, but we reduce our computation time. Let's see how much we reduce our computation time over here. Okay, now our computation time would be for 8-point DFT, what our computation time was. For n-point DFT, our computation time was equal to n square. So as this is n by 2-point DFT over here, so our computation time for this block would be equal to n by 2 whole square, whereas the DFT for odd entries would be equal to n by 2 whole square. Additional time that would be needed for complex computation would be for calculating these W8 terms, that would need an additional n number of complex computations. So in total, our number of complex computation would be equal to n square by 4 plus n square by 4 plus n. As we have said in our practical example, the value of n is extremely large, so hence n square would be way too large than n. Hence this equation would be approximately equal to n square by 2, as n is extremely large. So what we can see is that when we were using DFT, our computation time was n square, but by using divide and conquer rule, we had reduced our computation time by n square by 2, that is half of our total time. So by performing this technique, we reduce our time to half the time. Now, why should we stop over here? As we have done previously, that we have distributed our system into two equal parts, the even and odd part. So why don't we perform the same technique on our even entries and odd entries? What that would mean is that our even entries are written over here. We can further distribute it into our even and odd entries. Like our system over here, let me go to next slide and represent it over there. Like our system over here is written as like our function over here are represented as x0. We have four terms: x1, x0, x2, x4, x6. Now what we can do is we can further distribute this function into even and odd entries. Now although all these terms are even, but if we represent the order of this system, our even entries would be basically, these two terms would be our even entries, whereas these two terms would be our odd entries. So if we are trying to represent our system into separate even and odd entries, what we will do is that our even entries would be x of 0 and x of 4, whereas our odd entries would be x of 2, x of 6. Now, as we know that our general formula was x of k was equal to f of k w and k g of k. Now, using this formula, and as I have shown how we will distribute our even and odd entries, try to draw the butterfly diagram that we have already drawn in the previous slide. Just pause the video over here and see how you will draw your butterfly diagram. Once you have drawn your butterfly diagram, then play the video and see what I am doing. If our values match, that means that you have understand what butterfly diagram is. So you can draw the butterfly diagram by yourself. Okay. If you have drawn the butterfly diagram, what it would look like would be something like this. This is basically DFT and 2-point DFT, basically 2-point DFT. Similarly, this block would also be another 2-point DFT, and the answer that we will get over here would be basically f of 0, and the next term over here would be equal to f of 1, whereas the odd entries over here would be equal to g of 0 and g of 1. Now, according to this formula, what we will get would be, let me draw 4 straight lines. Okay. Now, what we will get over here is that our x of 0 term would be equal to f of 0, as this is 4-point DFT. So our term for x of 0 would be equal to x of 0 would be equal to f of 0 plus, and there is a plus sign over here, plus w4 k g of 0. This k is also equal to 0, so we will write w40, f of 0 plus w40 g of 0. So our x of k, x of 0, what we have to do is that we have to draw a line from there to there, which would be multiplied by the term w40. And we need to draw arrow over here. Now our x of 1 term, basically that term would be equal to f of 1 plus w41 g of 1. Now, redrawing that would give us something like this. And the term that it would be multiplied would be w41. Now, x of 2 term would be basically equal to, rewriting that for your convenience, x of 2 would be equal to f of 2 plus w4 to g of 2. So x of 2 is equal to f2, that is equal to f of 0 plus w4 to g of 0. So what we have to do over here is something like this, whereas our bottom line is multiplied by w4 2. Similarly, this line would be multiplied by this, and the bottom line would be w4 3. In this term, we will calculate x of 3. I'm using a laptop, so it's difficult to draw over here, but you get the general idea how we will draw the diagram. Let me show you a neat and clean diagram. It would be similar to what I have drawn over here. This is a better view of what we will get over there. What we have done is that we have distributed our function into even part and our odd part. Now those even part, we have calculated 2-point DFT of that, 2-point DFT of that, and those terms f of 0, f of 1 are added with g of 0 and g of 1 with the multiplication of factor w8 2 and w8 1. Oh, one more important thing that I forget is that what I have while drawing the function, what I did was that, okay, let me rewrite the formula. What I did was x of k is equal to f of k plus w4k g of k. For x of one term, that would be an easy example to understand. For x of one term, what we will do, what we get was f of 1 plus w41 g of 1, and when we multiplied it, we multiplied it with w41, but over here we are multiplying it with w82. So how w41 is equal to w82? We can see that by drawing a unit circle diagram, and I have already shown you that those two variables are equal. In unit circle diagram, this is equal to w80, this variable is equal to w81, whereas our negative imaginary term, that is equal to w82. And when we have to calculate 4-point DFT, this was, our first term was equal to w40, and our second term was over here, which was equal to w41. So what we can do is we can write w41 in terms of w82, as we are calculating 8-point DFT. So initially we were calculating 8-point DFT, so we have to convert all our variables in w8 forms. So that's why while drawing our diagram over here, all these variables were initially w4 with some power, but we have to convert them to w8 form. Okay. Now this was our basic diagram that we had been using for calculating 8-point DFT, this complete diagram, and what we did was that we reduced this part by calculating 4-point DFT that we had done in the previous slide. So what we can do is that instead of using this point, we can place the example that we had provided, in previous slide. We can replace this part with that. Similarly, our odd terms could also be changed. You can again try that at home. I won't show you how that is done, but that thing would be visible when we will be drawing our next butterfly diagram. You can see it over there, but for practice you can do that by yourself. By replacing this value in this diagram, what we get is something like this. This is our basically the even part of even entries. Sorry, would be the even part of even entries. This would be odd part of even entries. This would be odd part of even entries, and this would be odd part of odd entries. So in this way, we reduce our 8-point DFT. We distributed that into 4 different parts. And we reduce our computation time. If we see our computation time over here would be basically, for the first block would be n by 4 whole square. Similarly, second block n by 4 whole square, third block n by 4 whole square, fourth block n by 4 whole square. So in this manner, we will keep on reducing our computation time by the number of iterations that we perform, how much we distribute our function into parts. Now, if we have something like, if we are trying to calculate 16-point DFT, it's not mandatory that we have to perform this iteration 3 times. For a 16-point DFT, we have to perform this iteration 4 times until we get 2-point DFT. Our end solution would start with 2-point DFT. Now, one point that we need to remember over here, I've already told you that, or I've already told you and given you a quiz about that, is that if we are trying to calculate DFT for some point, like if we are trying to calculate DFT where you have like 13 variables, how would you calculate a 16-point DFT of that term? What we usually do is that we add 0 variable in the end to make it 16 variable. To calculate 16-point DFT for 13 different number of a series of 13 number, what we usually do is that we add 3 zeros in the end to make it a series of 16 different variables, and then we calculate DFT of that series. So if you have like 1000 points and you need to calculate FFT on that, what we do is that we add 24 zeros into the function, into the series, and our series length would be changed to 1024, and using that our FFT would be reduced into, radix 2 form. That is, in the end our function would be the calculation of 2-point DFT. Now there is a radix for DFT also in your book. I'm not going to teach you that, and it's not even in your exam, but you should know the general idea what a radix 4 diagram would be. Using the ideology of radix 2, a radix 4 diagram can also be drawn. Now moving to some interesting part is that what is the advantage of moving it to 2-point DFT. Why did we stop over here? How 2-point DFT would make our life easier. Let's try to show me that. Consider this is a series that we need to calculate 2-point DFT. We have already done that, so I'm going to do that with a little bit speed. What we have to do is that when we are trying to calculate 2-point DFT, our series is written something like this: n of 0, n minus 1, x of n, w, n, and k. For term k is equal to 0, what we will get is that summation n is equal to 0, whereas n in this capital N is equal to 2, so n minus 1 would be equal to 1. So 1 x of n w20. Now this w20 would always be equal to 1. We can also see that in a unit circle this would be equal to w20, whereas as this is 2-point DFT, we have to distribute our function to 2 equal parts. This would be w21. w20 would be equal to 1. This variable would always be equal to 1, and this variable would always be equal to minus 1. So how we can reduce is, for k is equal to 0, our answer would be x of 0 would be equal to x of 0 plus x of 1. For k is equal to 1, what we will get, our summation series would be reduced to n is equal to 0, 1, x of n, w, 2, 1. The 1 would remain same, n. So this series would be reduced as x of n, x of 1 is equal to x of 0, w20 plus x of 1, w21. This term was equal to 1 and this term was equal to minus 1. So our answer is equal to x of 0 minus x of 1. So by this, what we can see is that our DFT for 2-point is extremely simple. Our x0 term basically is equal to x0 plus x1, whereas our x1 term is equal to x0 minus x1. If we want to draw that on butterfly diagram, instead of using this plot diagram, how we can draw, it would be drawn something like this, where this x0 term, is equal to x0 plus x1. So x0, this is plus 1 sign, so x0 plus x1, whereas our x1 term is equal to x0 minus x1, hence this minus 1 sign is used. So instead of using length to DFT block in every diagram over the previous butterfly diagram that we had drawn over here, what we can do is replace all these 4 blocks with the butterfly diagram. This is how it would be drawn. One more interesting fact is that let's draw a unit circle diagram and let me define you what the other interesting fact is. This is our W80, this variable is W81. The next variable over here is W82. Now this variable over here is W83, W84. The next variable is W85. This term is W86, and this term is equal to W87. Now what we can see is that W86 is the negative of W82. So what we can write is that W86 is equal to minus W82. Same goes for W81 and W85. Those are negative of each other. Similarly, W80, W84, they are negative of each other. Similarly, this series goes on and on. So what we can do over here is that for this term, what we can do is our term W82 and W86, if we move the W82 term back, what we have to do, like over here we move the W82 term back, our above function would be multiplied with 1. So that would mean we would get, instead of 1, if we multiply this, we will get W82 term over here. Whereas in the bottom term, we would get minus W82 term. And as we can see, minus W82 is equal to W86. We can change it to W86. Hence, both of these diagrams are same. So, to reduce the number of computation that we need, what we can do is that instead of using W82 and W86, we can move them back, and instead of calculating two different variables over here, we would just need to calculate one variable over here, that is W82. So using that, what we can do is, this W82 term and W6 term, both of these terms would be moved back, and this would be +1, and the negative, we will get -1 over here. Similarly, W80 and W84, W80 would move back and this W84 would move back. This would be multiplied with one term, and this line would be multiplied by -1. Same thing would go over here. W80 would be moved back. Similarly, this W82 would be moved back. Sorry, W84 would be moved back. W80 is moved back. This term is multiplied with 1. W84 is moved back. This term is multiplied by -1. Same would go with W81 and W85, 2, 3, 6, and 7. So once we perform that computation, what we will get in the end is something like this. Basically, this is our final radix to butterfly diagram. Now you don't need to remember each and every step that we have performed over here. As an exam, you won't be asked something like that. You don't need to explain how your radix to butterfly diagram is created. You just need to understand how it is created and what would happen if we have to create a butterfly diagram for 16-point DFT. If you would have a written quiz, you won't be asked anything like 16-point DFT, but if you are given a home assignment, in that you could be asked to draw a butterfly diagram for 16-point DFT. So the same technique would be used even for 16-type DFT. You can see a pattern in this 8-point DFT. that pattern could be followed to create a 16-point DFT. For 8-point DFT, we use 3 stages. In 16-point DFT, we would use 4 stages. For 4-point DFT, we would use only 2 stages. 8-point DFT, our numbers are distributed into even and odd in this form, whereas for 16-point DFT, there would be again our number would be distributed into even and odd terms. You just need to understand, you just need to keep on changing them so that you can get what your series would look like, and the same thing would keep on happening. So basically this is your radix 2 butterfly diagram. Now the advantage of radix 2 butterfly diagram was that it reduced our computation speed. Now one interesting thing about radix 2 butterfly diagram is that interesting question basically I can say is that how we will get this series, a series that is distributed into even and odd term. How we will get that series? Computer student might know that the answer to this question, but let me show you that how we can get something like that. So there is a command that every computer student is known as bit reversal. Let me represent all for 8 bits. What we will do is for 0 we will do 0 0 0. For 1 we will write 0 0 1. Then we will write 0 1 0 0 1 1 1 0 0 1 0 1. This is 2 3 4 5 6 and 7. Now what bit reversal do is that it reverses your series of your bit. Like in bit reversal 0 0 0 would remain as 0 0 0, but your bit 0 0 1 would be changed to 1 0 0. Your 0 1 0 bit would remain the same. Your 0 1 1 bit would be reversed as 1 0 0, whereas 1 0 0 bit would be changed to this term. Let me write down every term and then see what each term represent. Basically this is 1 2 4, so this would be 0. The next term would be 4 2 6 1 5 3 7. So by using bit reversal, what we did is that our series are arranged in the manner that we want. Our first term is x0, our next term is x of 4, the next to that term would be x of 2 and x of 6. This is what we need in butterfly diagram. This is how our series need to be managed when drawing butterfly diagram. Now our MATLAB does perform every time we need to calculate DFT. Our MATLAB perform radix 2 butterfly diagram, but it does not draw a radix 2 butterfly diagram. What it usually do is use this matrix reduction technique, and using this matrix reduction technique it calculates your DFT. What this matrix reduction technique you can see is that these are addition of your, basically this is an identity matrix which is of length 4 by 4. The second identity matrix is also of length 4 by 4. This is also 4 by 4 and this is also 4 by 4. This matrix is also of length 4 by 4. This is also of length 4 by 4. So what we can see is that this is addition of 2 terms, whereas this is subtraction of 2 terms. And if we look at our butterfly diagram, what we can see is that these two terms are basically addition, whereas these two terms are basically subtraction. So a butterfly diagram, basically each stage of matrix is created using your butterfly diagram. The next stage is drawn using the next matrix, basically your next matrix over here. This matrix is drawn using your next stage, that would be this stage, and the third matrix is created using this stage. So what would we do over here is that, let me show you what your F4 term would be equal to. Let me draw a 4-point DFT, the matrix technique for 4-point DFT. Let me show you that, so that as we have small area on this page, so it would be easier for me to draw a 4-point DFT matrix reduction, and you can, using the same technique, draw 8-point DFT. What we use over here basically is f of 4. What this f of 4 is basically the solution to 4-point DFT. What we get when we perform matrix reduction for calculating DFT. Let me show you what F4 would be equal to. Basically, F4 would be equal to, our first would be an identity matrix. This identity matrix basically is of 4 cross 4, but for F4 it would be equal to 2 cross 2. So identity for 2 cross 2 is equal to 1 0 0 1 1 0 0 1. The next matrix would be equal to 1 0 0 1 minus 1 0 0 1. This is our first matrix. Our second matrix would be equal to 1 0 0 1 0 0 0 0. This term would be equal to 0 0 0 0. Our Tuttle factor would be equal to W1 0 0, as this is for 4-point DFT. W4 with power 1. Now what we will use over here would be basically, this matrix would look like F2 0 0 F2. So for F2, what we will do is that we will represent it something like, basically what we will get is 1 1 1, and our next term would be W4 2, then 0 0 0 0. Now this term would be 0 0 0 0 1 1 1, W4 2. In this manner we can calculate f of 4. Now to calculate f of 8, what we have to do is that our matrix identity would be of 4 cross 4 length, whereas this matrix, the F4 term, would be calculated again using this matrix. So our F4 would be calculated again using this matrix, and to calculate that, what we can do is, instead of using this term, if it's difficult to calculate this term, we can write F2, and F2 would further be calculated using simple matrix reduction. Now what we can see is that most of our multiplication over here is with 1 and 0. The only term that would introduce some complexity would be W8 terms. So what we can see is that most of our computation over here are reduced due to the use of identity matrix. So basically this would complete our lecture on fast Fourier transform. Now our next lecture we would start basically on filter designing and filter structure. By this point I have completed everything that I want to discuss about DFT. So best of luck. Try to understand what DFT and FFT is, and later on we'll move towards fast Fourier and towards filter design.